Hey, John here. Let's do a quick review on what it means to measure the height of a tree so that we all remember. This one has a height of 1. And the rule is, how many edges are between the node you're asking about its height and the lowest leaf below it, right? Therefore, there's only one edge here. So these guys here, it has 2 levels, but the height is 1, right? If I add another guy down here, maybe Q, that height now is 2 because there's 2 edges to the lowest leaf. So the height, therefore, is formally defined as the number of edges to the furthest away leaf, okay? And you can say recursively that the height of B is equal to the height of D plus 1, okay? And, of course, you take the greater of the two when you talk about the height of B, because the height of this subtree down here, C would be a height of 0, B would be a height of 1 measured from here, but it's a height of 2 when you measure it from over there. So you say the height of B equals 2 because the largest chain to the leaf is 2. So how then do we write a program to measure the height of the tree? Well, as I said, the height is almost defined recursively anyway. It's the height of the largest subtree that is the 2 children plus 1. We already know how to recursively traverse a tree, and therefore we could probably use that logic to measure the number of edges rather than to visit the nodes and print out their values. What we'll do is we'll just count the number of edges in our logic. So let's start with the regular old recursion that we already know and love. So let's write a recursive function that can be called like this, like height, and then we're going to pass it like p root, where p root is, for example, the pointer to the root node in question. I'm going to erase that because that was a different tree, right? So here's my p root variable, and that would be like an address that points down here, okay? So that's how we want to call this thing. So what is it going to do? Height node star p, right? And this is just our regular standard tree traversal kind of logic. So we're going to say base case. If there's no p, then return. Okay, now we're going to return an int this time. And I'm going to, there's a few, the base case. We got to really figure this out and make sure that it makes sense. So I'm going to put a box here. It's not exactly clear yet what we want to return when there isn't a node. So this will become obvious later on as we go. All right, so what then do we do when it's not the base case? Well, we're going to ask for the height of the 2 subtrees. And we're going to say, hey, whatever one's bigger, that's the height of the node in question, and we got to add 1, right? So let's say int height of the left tree equals height, and you pass it p left, which itself may or may not be null, right? It's okay because that's where the base case comes in. And when you got an int height of the right tree equals height of p right. Now this will tell me, if we do this right, the height of the subtree at C and the height of the subtree at D. What do we do with all that? Well, you take the biggest one and you add 1, right? So return. What am I going to do? I'm going to say if height of left is greater than the height of right, then I will return the height of left. Otherwise, I'll return the height of the right tree plus 1. All right, that's all on one line. You know how to use the question mark operator, right? You ask this question. Ruined my question mark. You know how to use it, but I don't know how to write it, apparently. So you got height of left is greater than height of the right. If that is true, then this expression here is evaluated, and the value of this expression as a whole is that 1. And if this is false, then this expression is evaluated, and the value of the thing in parentheses becomes the value of HR. If then else, with a lot less vertical waste of space in your code, right? And then we add 1 because the height of the current node is 1 more than the longest height of the 2 children. So what do we put in here? Like, maybe 0 would be a good idea, or something like that. Well, this all depends on what it means to ask for the height of a tree that has no nodes in it, right? Well, if the height of a tree with 1 node like I erased over here, that one with A, and I said the height of that is 0, in the height of like A and a B in here, this would equal a height of 1. Okay, well, if we just simply walk this back, if that's a height of 1 and I erase that and I got a height of 0, if I erase that one there as well, then one would argue that this is probably the height of a null pointer would be -1. And that's true in order for our math to come out right. So let's kind of walk through this and make sure we got the right thing. Let's find out what happens if we pass in the p root. Let's say we have our p root and it is null, okay? What will this thing return? Well, if p root is null, we come in here. This is true, therefore we return -1. So the height of a tree that has no root at all, like I said, let's just declare that as having a height of -1, okay? That's reasonable. It's an empty tree. So, and we do that only because if we have a height that has a single, or rather, if we have a tree that has a single node, we say, what's the height of that? Well, let's see what happens in here. So we come in here, is p root null? When we call it with p root, is the first call to this height function. Got a null pointer? No. So it comes down here and it says, what's the height of the left tree of A? Well, this left pointer is null, and the right pointer, as we know, is null based on that definition, right? So this function here will return a -1. And then it'll come back and it'll say, hey, what's the height of the tree on the right? Well, that's another one that's null, so that'll come back with a -1. Is -1 greater than -1? No. Then the value of this expression as a whole is HR, which is -1, plus 1, which is 0. So this function will return a 0 back up here, and that would say the height of this tree as drawn here will equal 0. And that is the correct value for that tree. So this checks out. This looks like a good default value here. So let's see if it works when there's children in here, right? So B, maybe, let's put a C over here and a D in there. So this one hopefully will end up with a height of, what, 2, right? So let's say we started off p root pointing to A. We come in here, it's not null. What's the height of the left tree, okay? So let's keep track of where we are. I'm going to just say A is making that call right there, right? So this will invoke the height function recursively, and it'll pass it the address of B because that's the left child, right? So it's not null, and the B will come along in here, and he will then make this same call. So now we have, in the recursive stack, we have both A and B are executing this line of code, nested. So it comes in here, B asks about his left child. Left child in this drawing is null, right? So it's going to return this -1 for HL when it's called for B. And then B will move along. And, oops, I got the wrong color. Yikes. So now B will make that call for its right child. Well, we know that the right child is null as well. Therefore, it's going to go in here and it's going to return a -1. And we just went over this scenario where both of these are -1. This is going to return a value 0. So the height of B is going to say, hey, I look like I'm 0, which is right for a node with no children, which you just talked about before. So B is done. He then returns back to A and he returns the value Z. So A returns from this function call here already in progress, right? From the recursive call, and A is then going to move down here and he's going to make his call to the right side. Well, what happens on the right side? Well, same thing that we just saw happen with B is going to happen now with the right child. Okay, so when he comes in to call height passing it C, C is not null. C is going to say, hey, how big is my left guy? Well, C is going to call height and pass it the D. Okay. D is going to come along and say, hey, I'm non-null. How big is my left guy? Well, my left guy is null. So he's going to end up with a 0 for there. He's going to come back with a, well, actually a -1, right? He's going to be -1 for here, -1 for there. Then he's going to do this, and he's going to say my height is 0, okay? And then he's going to return to the height function already in progress from executing for node C, which is just returning from this call here, and C then moves on to his right child, which is null. So HR will get calculated by coming in here. So this, for C, this guy will say he's -1. This guy down here said his height is 0, okay? So C then comes along and says, well, which one's bigger? Is my left one or the right one? Well, he says my left 0 is bigger than -1. Therefore, this thing evaluates to 0 plus 1, which he says, hi, my height is 1. C is now done, and he returns the 1 back to A. So A ends up with left guy reporting back a 0, the right guy reporting back a 1. Therefore, this will evaluate to HR being larger. Therefore, it'll be 1 plus 1, which is 2. So A will then say, my height is 2, return back up to here. This guy will return a 2 when it's called for this tree. And you can walk through this for other scenarios you want. As written, this recursive routine will always return the height of any binary tree. So what does this have to do with level order traversals, right? Well, okay, so let's now talk about how you traverse in level order when you don't have your tree stored in an array like we did in the previous video, right? So let's draw up a tree, and I'll mark them in level order. So these will be sorted. So A will come out first, then B and C. So this would be if we traverse the level tree in level order from left to right, you know, and top to bottom, left to right, right? So then you'd have maybe a D here, maybe you'd have an E, and an F. So make it interesting, right? It's not a perfect binary tree. These are labeled in level order A, B, C, D, E, F. So what you do is you just run across horizontally on each level one at a time. So let's write a function that will traverse this tree in level order if it's stored as a bunch of linked together nodes rather than putting it into the array that we want through in the last video. Now you'll know why we did the height function. So what does it mean to do this? Well, what we want to do is we'd like to write a function that says, hey, go down as many levels as we need and then wander across, printing the nodes. Well, if you think, again, this is another kind of a traversal, and all these recursive routines so far have kind of come in handy, right? So let's look and see how a recursive version of one of these traversal routines could be used to do this, right? Because if you think about it, if I just traverse this tree and I keep track of how many levels I've gone down as I walk through the tree, and let's say I want to print out all the nodes at level, at depth 1, okay? So I could walk through my tree and, in order, post order, whatever I want to do. And I could just keep track of how many levels I've gone down as I walk through the tree. And if I'm ever on level, depth level 1, depth 1, then I print out the node. And obviously, I don't need to even look down below the level I'm wandering across right now. So basically, what I really need to do is write a traversal that counts how many levels I've gone down from the root. And if I'm down at the level I want to print out, just print out the value and ignore the children. That would work, right? So let's have a look, see at what that recursive routine might look like. So let's just call this one like level order. All right, so what are we going to do here? We're going to level, maybe we'll call it lev, right? And we're going to node star P, and we'll just fill in our usual recursive routine. Well, somehow we need to know the depth we need to print out, right? So obviously we need another parameter, I'm just saying, okay? So if I just put D for depth, right? So this is going to be, how do I measure and print out all the nodes at depth D, right? Okay, so there we go. What if we have a null pointer? Well, again, we always have these base cases, right? If there's nothing to do, then presumably we certainly can't print anything. So no matter what, we need to get out of here. We'll make this void because it doesn't actually measure anything. It just, it's going to print in this case. All right, so what then if P is not null? What are we going to do? Well, in this scenario, the only time that could happen is when I'm on these 3 nodes up here. So on the first call, when I've got a pointer to the root node, I'm not on the level I want to be printing out, right? And D equals 1. So how is that all then going to work? Well, I can simply say if P, or rather D, if D is not 0, I'm going to argue we're not down at the level we want to be. How do we get down there? Well, we're going to call level traverse for P left. And we're going to say, I want to print the node values out at depth D minus 1. So what this will do, because A was entered, we're walking through for node A, when P points at A, when it calls level P left for D of D minus 1, this will now be entered with D equal to 0, and this if will be false in that scenario. Okay, I'll leave a little bit of room and say else, what do we do when D is 0? Well, that happens only when I'm this many levels away from the root. So that's the one I want to print out, right? See out, double left P value, and I'm basically done. All right. But what about the right trees? Well, yeah, you can imagine that you'd see the same kind of recursion in here as everything else we've ever looked at. Oh, this is the right one now. D minus 1. Okay, this is basically how you do it. So, or this is one way you can do it, right? Because you could use the array method I talked about earlier. But if you're not in a situation where you could create an array just for the sake of traversing it, if the tree is already built using a linked structure like this, converting it into an array just to be able to print out something in level order might be an inefficient thing to do. This may be a better way to go about it. So, again, let's think about this for a minute. What happens when we're in A? We just walk through that. So D is non-zero when it's called the first time. And the 1 here represents, here's how many levels away from A I want to go when I print all these nodes out. So if it's not 0, we say go to the left node and say print out a level this many levels away from the node that I'm passing in. I'm passing in a B, and this is 0, so don't go anywhere. Just print this guy out. And he does. He says, I'm B. Okay, great. Then he does that here, and he returns, and then A is returning from this function here, and it will then execute. Okay, now I got to go on my right child. And I'm going to do the same thing, and I say, hey, you print out all the keys this depth away from where you are, and he's going to be given a 0. So in that case, when he's entered for C, D will equal 0. That's false. He prints out a C, and he's done. He then returns back to A, who gets finished executing this and falls off down here, and he's all done. So that would print out this row here. How do we print out the row down here? Well, we do the exact same thing with a level of 2. So what happens, obviously, in that case, D is 2. When A comes along, this is true, and he says, go deal with my left at D minus 1. And this time, he's going to be called for node B, and rather than be giving a 0, he's going to be given a 1. So when B comes along in here, D will equal 1. This will be true. So B won't print out anything down here. He'll go to his left child down here and say, hey, I need you to print everything out 0 away from where you're at. Well, D then comes in here. D is 0. Therefore, it prints out his D. Okay? He's done, returns back to B. B just finished executing this. He then does it for the right child, which is null, which comes back, does nothing. So B is then done, comes out down here, returns back to A. A just finished processing his left child. A then comes along to process its right child, which is C. And remember, in A, D was called Lev was called when D was 2, right? So when he calls for C, calls Lev on behalf of C in this line of code right here, he's going to pass it a 1. C comes in, D is 1, therefore C tries to go to his left and passes it down a 0. So this guy is given a 0, comes in here, D is 0, he prints out his key here at E. It looks like my pen needs a little work. And he returns back to C, who just finished his left child. Then C executes this to deal with his right child and passes that a 0, just like he did when he was on his left child. F gets a 0 and does the usual thing for a 0 by printing out his value. And we've just traversed the bottom level of this tree. All right. So given this routine, this simply will recursively walk the tree and print out from left to right an entire level's values. All right. So how do we then traverse the entire tree? Well, if we have that function and we have a height function, it's not really that hard to do, right? What do you need to do? You just need lev. What do you got? P root, comma, 0. That will print out the top level, right, at depth 0, and that'll cause A to print out, and A won't bother to look at any of its children. You then need to call lev for P root 1, then P root, comma, 2, and so on for as many levels as you have in your tree. Well, that's just a loop with a counter, okay? So now how do we compress the whole thing down to traverse the tree, the entire tree in level order? Well, let's write our loop here. For what? Int I equals 0, because that'll be the 0th level, then the level 1, then level 2. I less than something, right? These are semicolons, and then plus plus I over here. All right, there's your lev of what? Each time you call lev, from the top level, to say first do the 0s, then do the 1s, then do the 2s, you're going to just pass it P root every time, right? And I. This will take care of it as long as you know what the heck goes in there. Well, what does go in there? What goes in there is the height of your tree. And we just wrote a routine to calculate the height of the tree. So this tree height is 2. This needs to go from 0 to 2, right? 0, 1, and 2. It needs to do 0 to 2. So you would either put a 3 in here, right? Because that's a less than. Or I could say less than or equal to 2. Because I have to execute it 3. Yeah, the loop has to run 3 times, obviously, right? So what I could do is put a call to my height routine in here, but that would be outrageously inefficient because every single time this loop goes through, it'll do a recursive walk of the entire tree just to measure its height, which is absolutely nuts. So let's call, if I can think in order, int, let's call this h for height equals height of P root. Then this simply becomes H, and we're done. So now we have all the code we need to print out the tree in level left to right order. So we can call this one like lev LR and give it P, node rather, star P root. And there you go. There's my print out the entire tree in left to right order by level. Done. Thanks for watching. See you next time.